All right, for this explainer, we're going to be chemical detectives. We're about to uncover the secret lives of the elements that are all around us. And I mean, really figure out why some of them stay perfect for centuries while others just crumble away. And it all kicks off with a really simple question. Have you ever wondered why a gold ring can be passed down through generations and it still looks brand new, but an iron nail you leave outside for a few weeks turns into this flaky brown mess? I mean, they're both metals, right? So what's the big secret? What's going on with their personalities? You know, this mystery is literally everywhere you look. It's in the shiny pots you cook your dinner with. It's in the copper wires hiding in your walls, bringing you electricity. It's even in the graphite in your pencil that lets you write things down, and in that silver spoon that gets a little tarnished over time. Every single one of these holds a clue. So like any good detective story, our investigation starts with the most obvious clues, how these things look and feel. These are what we call their physical properties, the first impression they give off. Okay, so at first glance, the case seems pretty open and shut. We can sort pretty much everything into two big groups. On one side, you've got metals. They're usually shiny or lustrous. They're malleable, which just means you can hammer them flat, and ductile, so you can pull them into wires. Plus, they're great at conducting heat at electricity. On the other side, you've got the nonmetals. They're usually dull, they're brittle, and they're awful conductors. Easy enough. Case closed, right? Well, not so fast. Just think about how extreme some of these properties are. That ability to be pulled into a wire, it's called ductility, and gold is the undisputed world champion. Get this, a single gram of gold, that's about the weight of a paperclip, can be stretched into a wire 2 kilometers long. 2 kilometers! That's just insane, and it's a massive clue about what makes a metal a metal. But just when we think we've got our neat little categories all sorted out, we meet the rule breakers. You've got mercury, a metal that's a liquid. You have gallium and cesium, metals that will literally melt in the palm of your hand. And then there's iodine, a nonmetal that's shiny. Or graphite, the stuff in pencils, a nonmetal that actually conducts electricity. And some metals, like sodium, are so soft you could cut them with a butter knife. So, clearly, looks can be deceiving. To really solve this thing, we have to dig deeper. We can't just trust what's on the surface. We need to see how these elements act, how they react with other things. This is where we find their true personalities. And the absolute key to their personality is this one concept, reactivity. It's just a measure of how eager an element is to jump into a chemical reaction. It's kind of like people, right? Some are social butterflies, desperate to react with everyone, while others are total introverts, happy to be left alone. This one idea, it explains everything. So how do we test for it? A fantastic way is to just throw them in water and see what happens. It's like a series of strength tests. The most reactive metals, guys like sodium, they go absolutely bananas in just cold water. To get magnesium to even notice, you gotta heat the water up. And for the really tough customers, like iron, you have to bring out the big guns, steam. And then you have the elements that just refuse to play the game at all. Gold, silver, copper, they won't react with water, period. Doesn't matter how hot it gets. Now that is a huge clue that brings us right back to our original question about that gold ring, doesn't it? So, after watching how all these different elements react with air and with water and with acids, scientists started to see a crystal clear pattern emerge, a ranking, a definitive list that solves our entire puzzle once and for all. And here it is. This is the master key to understanding pretty much all of metals, the reactivity series. Think of this table as a power ranking for metals, like a league table. At the very top, you've got potassium, the most reactive of them all. And as you go down the list through sodium, iron, all the way to the bottom, that reactivity just drops and drops. And way down there, at the very end, we find gold, the least reactive metal. So here's the solution to our mystery. A gold ring stays perfect because it's chemically, well, it's lazy. It doesn't want to react with anything. Iron, on the other hand, is higher up the list. It's much more willing to react with the oxygen and water in the air, and that's what we call rust. And this isn't just some abstract list you memorize for a class. No way. The reactivity series is like a treasure map for all of humanity. It tells us where to find metals and, crucially, how hard we're going to have to work to get them. Yeah, this series is the absolute foundation of the entire science of getting and using metals, a field that we call metallurgy. And it makes perfect sense. This hierarchy tells us exactly how we get these metals. The super unreactive ones at the bottom, like gold, they're so stable we can literally just find them lying around in their pure state. Metals in the middle, like our friend iron, are found in ores, and we can get them out using heat and carbon. But the super reactive metals at the top, they hold on for dear life. So we need to use powerful electric currents, a process called electrolysis, to force them to let go. And we can use this whole reactivity thing to our advantage in some pretty amazing ways. Because aluminum is more reactive than iron, it can actually just rip the oxygen right off of iron oxide. This reaction, it's called the thermit reaction, releases so much heat that it produces molten iron right there on the spot. It's so hot, we actually use it to weld massive steel railway tracks together. How cool is that? Okay, so we understand their secret personalities. We've cracked the code. What's next? Well, the final step is using that knowledge, using it to improve on nature and prevent the exact kind of decay our whole mystery started with. And that brings us right back to our poor, rusty nail. This experiment shows it perfectly. See the nail in test tube A? It's got both air and water, and boom, it rusts. The nails in B and C, which are missing either air or water, they're fine. Corrosion, which is what we call rust, is just a metal reacting with its environment. And now we know all about that. So, what's humanity's best solution to this problem? It's the alloy. By mixing metals together, or mixing a metal with a nonmetal, we can create brand new materials with way better properties. It's like building a super team of elements. And you use them every single day. We add chromium and nickel to iron to make stainless steel, which, as you know, doesn't rust. We mix copper and zinc to make brass. And yeah, even that gold ring we started with, it's probably an alloy too. Pure 24-karat gold is way too soft for jewelry, so we add a little bit of copper or silver to make it stronger. And believe me, this is not a new idea. On the left, you see iron's natural fate, rust. But on the right, that's the famous iron pillar of Delhi. It's over 1,600 years old, and it has been standing out in the open air this entire time without rusting. It's an absolute testament to the incredible skill of ancient metallurgists who figured out how to create this stunningly pure and corrosion-resistant iron alloy. So from a simple question about a ring and a nail, we've uncovered the fundamental rules that govern the elements. We've learned how we pull them from the earth, and we've seen how we can combine them to literally build a better world. It really makes you wonder, doesn't it? Now that we've cracked the code of metals, what will humanity learn to master next?